too long because we've already talked about it a little bit. So remember we said that in an AC circuit we have this stuff called inductive and capacitive reactance. And that frequency affects both of them in an opposite direction. So we said for the inductor or the coil, anything that's a coil, meaning it's a coil like this, the more I cause the frequency or the electrons to either go back and forth or even pulse in DC, the more I try to change the current, the more that magnetic field is going to expand and contract and resist that change in current. Whereas in a capacitor, we said, if I don't change the current, if I just keep it DC, one plate's going to charge up, the other plate's going to empty out, and no current's going to flow. So, but the faster I change the current back and forth, the easier the energy or the power of that current is going to be able to transition through those plates, even though the electrons themselves don't actually cross the plates. So the capacitor, we said, loves frequency, and its reactance to the circuit will go down as frequency increases or go up as frequency decreases. The inductor, we said, doesn't like change. Its reactance or imposition to current flow will go up as frequency increases and go down as frequency decreases. So the two behave opposite of each other, which means the two can cancel each other. Okay? That in and of itself is pretty easy. We wouldn't need a whole lot of math to be able to figure things out. The problem is we sort of have to look at the behavior of both of these to see how they react with response to resistance, to be able to calculate total impedance on the circuit. Okay, so we got to study these a little bit more. So we're going to talk a little bit about inductive reactance, and we're going to say that X sub L equals 2 pi times the frequency times the number of henries represented by capital L. Okay, the amount of magnetism. All right. If we come up with some value of X sub L, we can put the little ohm symbol next to it. And if we do that, we can say that for a series circuit, X sub L1 plus X sub L2 plus X sub Ln equals the total inductive reactance. We can say for a parallel circuit of inductors, we're going to have to use the 1 over 1 over formula, where we're going to do X sub L1, X sub L2, and X sub L to the nth, whatever. Right? That's just like resistances. And that makes sense. Okay, so we now have a formula. That's going to be the behavior of the travel around what's generating the AC in the first place, frequency, and then the amount of magnetism being produced. That gives us a value of impedance or imposition to the current flow. If you look at it mathematically, if I increase the magnetism, the problem is going to get worse. That makes sense. And if I increase the frequency, the problem is going to get worse. Or X sub L is going to get bigger in both cases. So mathematically, that's correct. The other thing that's going to happen is, I guess I can draw it over here, is if I look at my plot line and if I, let's do voltage. If I look at my voltage like that, Oh, let me put a little V there. Okay, if I look at that voltage, when I take the power source, I am the human power source, and I attach it to the coil, I attach it to the coil, what happens? Well, immediately on both sides of the coil, I've got voltage applied, right? The current starts flowing, but magnetic field has to build up, so it lags. It slows way, way, way down. It says, I'm not going to build up because I'm slowing down. So it's not going to, the current buildup isn't going to be instantaneous. Voltage, 100 volts, boom, I got 100 volts in that coil, across that coil. Current's going to start coming up kind of slowly. So the current is going to come on, lag, sort of out of phase somewhat. And we're going to say this is X sub L, and it's going to shift that direction from voltage. That's X sub L current, right? So it's going to shift or lag behind. You okay with that? Everybody get that? All right, now for capacitor reactance, we're also going to have a formula, but we're going to have to modify the formula because the behavior is backwards. Okay, so we're going to have to use a reciprocal formula. So for the reciprocal formula, we're going to say X sub C equals 1 over 2 pi frequency and capacitance as measured, what did I use? See? Capacitance as measured in farads. Okay, and a farad is a lot of capacitance as capacitance goes. So that means as the amount of capacitance goes up, the total imposition to current flow is going to go down. And as the frequency goes up, the total imposition to current flow is going to go down. Right? So that's now modeling the behavior we want. Okay? The other thing that we got to look at is when we hook them up in series and parallel. In series, well, let's do parallel first. In parallel, when I take two capacitors and put them in parallel, like this, what have I done? Can't I just go like this and say I made the plates a little bit bigger? I just increased the size of the parking lot by that much. So all I have to do is add them together. So in parallel, X sub C1 plus X sub C2 plus X sub C to the n gives you the combined value of capacitance. Whereas when I put them together in series, what I'm going to do, I can just put another capacitor right there. What I'm really doing is I'm increasing the dielectric. Okay? So what's going to happen is my total imposition is going to DC is going to go up, but to AC, the more dielectric I've got, the more it likes the higher frequency. So I'm going to have to use the 1 over formula in series. X sub C1, X sub C2, X sub C to the n. So you have to remember, for series and parallel with inductors, it's exactly the same as resistors. For capacitors, we've reversed the two. Okay, and there will be some test questions around that. I don't think I won't throw anything at you with respect to calculating any of this out. Now, the other thing that's going to happen is I am the human voltage source. I'm going to take and I'm going to attach my voltage to here. What's going to happen? Voltage, I mean, current is just instantly going to start moving into this thing. Electrons are going to come ripping out of here. Current's going to start coming into here. And the voltage will stay low and start ramping up. Take a while to start ramping up. So current will be instantaneous, and voltage will take a while to ramp up. Or, in this case, voltage is now going to lag behind the current. As soon as I touch the capacitor, it sees almost no resistance to that initial current. At the point that the voltage gets to maximum or battery voltage, current comes to a stop, doesn't it? And then when I reverse the leads, boom, voltage drops because the power source can only put out so much, current immediately starts going. So what's going to happen is current is going to go the other direction. It's going to lead the voltage. So in this particular case, it's going to lead, and this one's a little hard to draw. So in the case of X sub C, current is going to go the other direction with respect to voltage. So now if I got the same amount in a circuit, they would cancel each other out, right? Current's going that way. Now you're going to have to remember that a little bit. So there's a little device to help remember that. Eli the Iceman. So in an inductor, the little L, voltage leads current. In a capacitor, current leads voltage. Okay, we good with that? Both of these go away if I just have pure DC. But as soon as I start having pulse DC or all the way out to AC, this starts becoming a problem. Now the other question we've got to ask ourselves is what happens to this drawing as I change resistance in the circuit? Well, presuming I don't have an unlimited voltage supply, which you don't, no voltage supply is totally unlimited. In other words, if I have a battery and I load the circuit, the battery voltage is going to drop a little bit, right? Any kind of battery. Or coming out the wall. If I put a big saw on, I won't have 110 volts, I'll have 90 volts. Whatever, as I load it. So as I increase resistance, voltage is going to go up and current's going to go down, or if I decrease, the reverse is going to happen. But in either case, we don't really care which direction, up or down. What we need to say is, and I don't know if this is going to work, but we'll try it. With respect to changes in resistance, magnitude is what's going to change. This direction. Okay? So the peaks are going to get, and valleys are going to get taller or narrower. So in capacitive reactance, we go this way. Inductive reactance, we go this way. Changes in resistance, we go at 90 degrees to the motion of the other two. Right? Okay, so if we're going to plot some inductive reactance and some capacitive reactance and some resistance, we've got to come up with a way of plotting out how that's going to, where you're going to end up. So first thing I got to say is I'm going to go inductive reactance a little bit, capacitive reactance a little bit way back down here, and then resistance all the way out to here. And the actual total imposition is my starting point out to here. Okay? My resistance would have been up here, not down here. So I'm going to have to do something to figure out what that is. Well, if I've got my little diagram here, this is a terrible thing. Let's turn everything 90 degrees and go that way. We're going to say this is R, that's X sub L, and this is X sub C. So let's say X sub C is a little bit smaller than X sub L. So I've got, let's say, 50 units of X sub C, 100 units of X sub L, and 200 units of R. So I'm going to go, what are you provided at 50? Then they're going to work in opposite direction. 1, 2, 3, 4, 5, 6, 7, 100. Right there. Then I'm going to go 1, 2, 3, 4, 5, 200 out to there. Okay? That's the total impedance. And I got to go draw a line from here out to there. That length of that line is my total impedance. How do I figure out what the length of that line is? Can I make a right triangle here? Now I've got side B, side A, the hypotenuse or side C, and Pythagorean's theorem comes into play. Pythagorean said the square root of side A squared plus side B squared equals side C. So we've got direction this way, direction that way, direction that way. Turn it 90 degrees. I've got my little triangle. I can use that formula. You guys aren't liking this, I can see that. Well, but I can do it. So I'm going to change the labels to protect the innocent. We're going to say Z squared, Z for impedance. I have no idea what the connection is there, but that's what they use. Z for impedance squared equals resistance squared plus the difference between X sub C and X sub L. The truth is, it's mathematically a little easier to subtract the lesser from the bigger, so you don't get negative. But once you take a negative and square it, it's going to become positive anyways, right? Negative 2 times negative 2 is positive, whatever. Okay? So I can then plug all this stuff together and come up with total opposition at current flow. If the circuit has no AC, what's going to happen is the value of X sub C will go to 0. Or if the frequency is such that when I calculate X sub C and X sub L, they are the same, then it still goes to 0. Because this minus that, when they're the same, equals 0. So now, if this becomes 0, we're saying Z equals the square root of R squared. Well, the square root of something squared is it something. So that's why you don't, technically this applies to a DC circuit, it just becomes a moot calculation because the value of capacitive and inductive reactance went to 0. Now you might ask yourself, well, what do I care? I'll tell you right now, if I run over there, because I did it just before I walked in here and pushed the little button over there and get down to the value that shows me how much inductive reactance is occurring, what I'll find is that right now, for every 0.89 amps we're using here in this building, or let me put it in terms of watts, for every 0.89 watts we're using in this building, we're paying for 1 whole watt. So there's an 11% inefficiency going on right now as we sit here. Probably because of inductive reactance. The inductive reactance is usually stronger than capacitive reactance. Okay? So We're paying for that. You bet the power company's gonna charge us for everything, all the power they produce and drive down the pipe, they're paying for it. Or we're paying for that. And the fact that reactance is preventing it from getting here, do they want to keep it as low as possible? Yeah, because they want me to be happy. Otherwise, I might stop paying the bill. Actually, you guys are paying the bill, but okay. So we've said Ohm's law applies where you have components interconnected together, say in series. Solve for the impedance in that series component. In parallel, solve for the components in parallel. Then you got to bring the two together. Okay. So now I'm not going to get too deep into the theory of all of this, and I'm certainly not going to throw any of these circuits at you. I do have one. Okay, so another thing that can occur is there'll be some value. Let's say I've got 15 ohms at 60 cycles per second. I've got 15 ohms of capacitive reactance and 20 ohms of inductive reactance. If I lowered the cycle, because inductive reactance goes down when I lower the frequency, and capacitive reactance goes up when I lower the frequency. If I lower the frequency from 60 down to 55 or 53 or some number, there'd be a point where the ohms of inductive reactance goes down and capacitive reactance goes up to now they're both exactly the same. X sub C equals X sub L, it goes to 0. So the problem is if I change the frequency, it's going to mess a bunch of other stuff up. So rather than change the frequency, we're going to keep the frequency very fixed. And we're going to do our best to design the circuit to be resonant. So every time somebody turns an inductor on, we'll turn a capacitor on. Now, in truth, that in itself is also not entirely practical. Although I will tell you, the big green transformer that's sitting outside of David's office in the front that runs this building takes the 5,000 volts and kicks it down to 277 volts, as well as these little bitty gray transformers all around. They also have big capacitor banks in there. And they're designed around what the expected loads are going to be in general. It's not going to be exact, and that's why the power factor is off a little bit. So they're going to inherently try to design systems to be a little bit balanced. As well, the power company is also going to have its ability to adjust. So a lot of times when you see that big green thing and you say, wow, transformer, it's actually both an inductor transformer as well as capacitor banks. And oftentimes when you see the one on the telephone pole go ba-boom and explode in a big bright flash, it's usually the capacitor that's exploding, not the transformer. Okay, so if I have some inductive or capacitive reactance left over, and that's impacting the circuit, there will be a ratio between true power, which is what I'm actually using, all the lights, the motors, the heaters, and apparent power, which is going over and measuring the amperage and the voltage and multiplying times each other. So the apparent power coming out of the power plant to you, I'll measure the two, multiply it, my apparent power is 100. Okay? But over here, what you're actually using in the building is 89. Right? There's a little bit of a loss. Well, the power factor is the ratio of those two expressed in a percent. Okay, so we conveniently got there because I picked 100. But let's say it was 10,000 and 809 or 8,900 and 900. Well, that would still be a power factor of 89%, right? Put it in terms of dollars. for every 89 cents you spend on power to power this building, you're also paying 11 cents for nothing. Well, after enough 11 cents, pretty soon you can say, maybe I could buy a couple of capacitors and reduce that. So I could pay for some systems to accommodate that.
Don't you always have losses though? I mean, regardless, just for operating. So,
you're going to do your best based upon predicted behavior.
in a perfect world, what would the best you could do in a power generation?
Well, it depends on how controlled the environment is. Okay, so on planet Earth, it kind of sucks. We know in the afternoon you're going to have a bunch of inductors in the form of ACs coming on. So we could get a rough average of design around that. And then we know, boom, things are going to go kind of wonky for a little bit during dinner. And then come night, the power is going to go down, but the lights are going to come back on. So we can predict some of that behavior and try to accommodate for it by turning banks of capacitors on and off or whatever. In an airline, it's completely different. In an airline, you basically got two states of being, right? Lights on, lights off. Okay? And the pilot controls lights on, lights off. So you may have the light circuit designed to where when it comes on, being that they're big inductors, they may also have some banks of capacitors come on at the same time. It's worth the wait. It may be worth the wait in fuel savings because you're going to save that much weight in fuel savings and operational cost and all the rest of that. So it sort of depends on how controlled the environment is. And you know, how much you're willing to invest in it. The important thing, I think, for you guys, I don't think you're ever going to calculate this, but you need to know that there is equipment out there put in place to accommodate this discrepancy. True power is what you use. It will always be less than apparent power. The only thing it can do is in a purely DC circuit is equal it. Can never get above it. Okay, and so whatever you need to memorize that. Apparent is volts times amps coming out of the wall, or going into the wall actually. And true power is what you've got doing work. So the resistive loads. Yeah, so here's an example of a picture I took, I don't know, some time ago. This actually shows the three individual phases and the power factor for each individual phase, and then the summative average of all of them. So in this particular case, we were losing 12%. All right? This shows the frequency, and that's that little panel up there, and they keep it pretty tightly controlled. It usually reads 59.99 or 0.01, sometimes it gets up to 0.2. But as soon as this starts changing wildly, phase and amplitude start changing wildly. This actually shows the relationship of voltage and amplitude and phase relationship. Okay? How much this is shifting in and out of phase for each one of the three phases. So, and note what's happening. My guess is the way they're trying to represent this is current is lagging, and it's an inductive problem. If we went into capacitive nature, these guys would shift and go the other direction, and they'd lead. Okay, that's just a graphic way of demonstrating the issue. So there's a problem. I went through this problem earlier. I don't think we need to go through that one. This is what it looks like when you have everybody reduced down to single components in series. However, when I go to parallel, I'm going to have to use my Pythagorean theorem. I'm going to have to put the 1 over in each one of these when I put these in parallel. Then it starts looking kind of ugly. Okay, note how I had to do, bring in all of those in the 1 over the rest of Pythagorean theorem, and then I had to do each one of those in there. So it gets really, really ugly, bringing the parallels together. I'm not gonna hold you, I'm not gonna throw any of those math problems at you. I just want you to understand, you can calculate what the total imposition to current flow. You'll find that power factor for most circuits doesn't get too much over 12%. If it does, we start looking at redesigning stuff. The other thing that's important to note, as Mr. Wexler was pointing out, anytime you run current through a wire, it's an inductor, right? It's creating some magnetism. Anytime you have current going through two conductors that are fairly close to each other, or very high voltage, there's a capacitive relationship between them too, right? So it always exists. That said, anytime you run a lot of current through a wire, you're going to get the wire hot, which means resistance, and you're going to create a lot of magnetism, which means inductance. So if I got to send a lot of power through a long, long wire, it makes way more sense to send a very, very high voltage, low current through that wire. Because now the only thing I've got around that wire is a very high ionized capacitor. And if I take the wire and keep it far enough away, separated enough, the capacitive relationship between those two and between those wires and ground isn't that great. So I'm gonna have to keep them kind of all up away from everything. So that's why those big, huge, super tall towers, they're tall and wide to keep the wires separated from each other, as well as keep them away from planet Earth, which will be part of the capacitor. But they're also operating at 100,000 volts, or some huge voltage up there, right? And if I do that, I will maximize transmission efficiency. Okay. All right, so let me, oh no, I didn't grab it. Oh, we're gonna go grab the quiz. I want to review the quiz before we go. No, I didn't do it. Next meeting.
I just had to like kind of visualize what we were talking about.
Oh, yeah. Once you find the current here, another current here this way.
So the way I found the current here, I realized that, you know, I have these, this voltage drop, so whatever it's left, this is how much voltage drop is going to be in the part 5. And that's how I, and then I found out the current here, and then I subtract these like this.
Good.
To review this a couple of times.
Yeah. Just have to play with.
Okay, you're gonna need a Scantron. There are 40 opportunities for success. And I know you guys are gonna take advantage of every one of them. There will be no blanks. I can't tell you how many times you guys leave blanks. Okay, pick something. All right, so you are going to need to know what a voltage regulator is. Might want to have a little familiarity with at least the 3-unit type voltage regulator and the carbon pile regulator. You're definitely going to need to know what the different kinds of generators are. AC generator, diode rectified DC generator, and commutator DC generator. What are the basic operating principles of each? So, where did it go? When I have a field like this, what do we call, what do we call the little metal piece in here? Armature, is this really the output portion? Isn't this the field? And the permeable conductor that sits inside it we're gonna call it either a shoe or a pole, or pole-shoe combination. Right? Okay, because it's a magnetic pole, right? North Pole or South Pole. Okay. Yeah, more voltage regulator. Let's see, there's the reverse current relay, the current limiting relay, and the voltage relay. Voltage regulating relay, so you need to know about those. Should know what the slip rings are, what the commutator is, what the brushes are, the brush springs. Should know what a diode is and what a rectifier is. Yeah, okay, there again some AC and versus DC questions. And I'm not going to say that one is better than the other. They both have pros and cons. In general, AC is a lot more convenient, but they really suck when you have to use a battery. It just don't work. So you need to know what full field diagnosis is versus flashing the field to establish residual magnetism. More voltage regulator, over voltage protection. What that looks like. Don't really do it in a DC generator because it automatically compensates for it. There was a couple of there are a couple of questions. Remember we looked at the carbon pile regulator and the equalizing circuit? So just have a little bit of sense of how that works. And more on rectifier. Okay, a couple of questions about capacitive and inductive reactance and phase shift. So with current, it's going to go one way in an inductor, the other way in a capacitor. So one of the things that's a little difficult about all of these systems that we've been talking about is some way or another I need to write about them and put some specs out. So that when you go to buy one and install it, you know you got the right thing. So with respect to a light bulb, what kind of specs are important to you? Well, you basically want to know what its operating voltage is and how much light it puts out. However, measuring light is sort of difficult. So it might be a little bit easier to say how much power does it use to put out light. So wattage might be useful. So operating voltage and wattage might be useful. In other cases, though, wattage may not be as informative as voltage and amps. We're always going to need to have some rating around voltage, though, because we're always going to have pretty fixed voltage in our systems. Okay, it's going to either have a 12-volt battery or a 20-volt battery, 24-volt battery, or it's going to be designed to operate around 100 volts or 110, or 200 volts or 400 volts, somewhere in there. And you can't get too far out of that ballpark. You got to stay fairly close to that. So voltage is going to matter. In the case of power generation, we typically are going to give you ratings of voltage and amps. Why? Because ultimately you're going to have to install this unit in light of a bunch of users on the bus that are also measuring amps. And you got to make sure that your generator puts out more amps than all the users can consume. So they have a tendency to do it that way, even though you could use power, right? The problem is you'd still have to have voltage. Because I can't put a 28-volt unit in a 12-volt hole. That would make for a big mess. Okay, so that's gonna be true of any kind of device. Either they'll give it to the form of power and or voltage and power, or voltage and amps. Tends to be the basic electrical specs put out. And then of course the resistor, they'll also give you the amount of resistance, power and resistance. Okay, so there are a few questions about inductors and capacitors, particularly with respect to how they impede or improve current and voltage flow. Also with respect to how they must be analyzed in terms of series and parallel circuits. So remember, resistors and inductors are the same, capacitors are reversed for capacitor reactance. Okay, and then a couple of basic DC questions. All right, so you guys are ready for the quiz next week. It's an easy one. Do study. Get your I strongly recommend the study guides. You know, ASA or Gleim or whoever study guides. Very, very useful. I don't mandate them, but I strongly recommend them. I think you can get derivations of them online for free if you're desperate, but you're going to need them whenever you go to get the rating anyways, right? Go take your written, so. All right, so let's take, I don't know, 10 or 15 minute break. I'll get the cabinets open. Looks like Mark's ready to do some Jenny testing. Then those